Hey guys, so it's serious talk time. I've heard you've been experimenting with some stuff. It's okay. It's okay. That's perfectly natural, especially while at college. Hell, I even experimented a little myself. It can be perfectly safe and fun, but you've got to be careful. I want you to know the facts and understand what you're getting into. I think it's time we had a talk about full bridge rectifiers. Yes, you've seen them in class, you've used them, but I don't think you've really actually dove deep into them yet. I don't think you've really looked at them and discovered what they have to offer. Yes, you can get a DC voltage out of them. We all know this, right? It's pretty damn simple. Everyone's done it. Let me bring up my pen here and I can show you. And change my color. Okay. So from here, obviously, you get this, right? We know that. We've done it over and over again, but I think there's more to it. So I'm going to look at it a little bit and see if I can help you guys understand what's going on. In order to do that, I'm going to have to start out with a little bit of circuit analysis and voltage review. I have a slightly different way of looking at circuits than you might have seen before, and if I just go over that real fast, it might help you. Maybe you'll like the way I do it. If nothing else, at least you'll understand what the hell I'm doing. I'll go over the standard usage, which gives you this output. We're all used to. Of course, it just erased that for some damn reason, but whatever. Then I'm going to go over the different kinds of voltages you can get out of it and different ways you can use them. And after that, finally, I'm going to show you how to efficiently use them, and hopefully that will help you with your project you're working on. Let's move on. Okay, so circuit analysis and voltage review. Start off, AC voltage. What is it? Yellow plus, yellow minus, little sine wave. This gives you a sine wave output, right? We understand this, but what does that mean? Like, what is a sine wave output? Well, it's a changing output, easy enough. Now, what about this part here where it drops below zero? What does that mean? How can you have negative voltage? To understand that, you have to understand how voltage is measured, like what it means. It is a potential between 2 points, right? So if I had the point, we'll do something simple, right? We have a battery. From plus to minus, we have 12 volts. This is a potential. We are saying if we consider the minus to be 0, then at this point we're 12 volts above that. So what if, let's change the color here. What if we decided that instead we're going to call this 0? So this is 0 volts. Stop doing that. That's 0 volts, right? And then here, we're going to call this the plus. The voltage hasn't changed. From here to here is still a difference of 12 volts. So that means that this point is 12 volts above this one. So we have negative 12 volts. Okay? So what does that mean? It means that the only difference between positive and negative voltage is the orientation at which it is measured. So if we were to take a simple circuit, should be doing this. The red's a little bit easier to read. Okay? Easiest circuit you can imagine. What that means is half of the time, blue, half of the time, current's flowing that way, the other half flowing that way. It alternates. So during this portion, which I call the positive half wave, and most people, other people do too, because I didn't come up with it myself, during that time, it's flowing the way you would expect. Up this way and around there, right? Then, when it's below 0, it's flowing this way. It is alternating. That's why it's called alternating current. It alternates directions back and forth, and you can't see where I'm pointing. Laser pointer. It's alternating directions, so it starts this way, and then it goes that way, and just keeps doing this. Just ping-pongs its way back and forth. What does that mean to us? Well, if we understand that, then we can start to understand circuits a little bit better for what's happening. So let's take a look. We're back to our circuit. This is the positive half wave. So what I like to do is I look at it and I try to figure out what the current's doing and how. So I say, okay, on the positive half wave, which has what I wanted. Bring the pin back up. So what's happening now is there is just a lump of voltage. I don't know why it thinks I'm right-clicking. A lump of voltage, a flat, and then another lump of voltage. Stop that. Okay, I must be not moving it far enough or something, and it thinks I'm holding it down in one spot, but I apologize for stuff popping up. And actually, I don't even think you're seeing that. It's just not doing anything. I should just shut up when it does it. Okay, so that is essentially a positive half wave. The negative half wave, we're not going to use on this one. I'll bring on the other one, but just so you can see it. I'm going to do that in a second. It'd be confusing here. I apologize. Not do that. Okay, so positive half waves traveling this way. Comes up through, comes up through here, travels down this path, goes here. It cannot go through this diode, obviously, because there's an X on it, right? So it has to go through this diode instead. Travels through, gets to this point. Can't go through this diode because there's a wall in the way. It can only go forward. So it goes this way, through the diode, up and around. Now, it doesn't want to go up, that takes it back to plus. It wants to go to the minus. So it comes back down, around, and out. Okay? That's how I like to look at circuits. I think it's very helpful for me to do so. So what happens on the negative half wave? Well, imagine that, I have a slide for it too. Alright, so I'm going to switch back to red and bring up the pen. Now, the negative half wave doesn't have that, right? Oh man, why? Sorry. This thing is not cooperating. So, we have the pen. This is not correct. All right, what we have is we have the negative here, and we have the positive here. Okay? So it reversed polarity. And then in that case, it's a positive lump traveling in that fashion. Right? Because you've reversed it, and now it's a positive voltage just going the other direction. So that means it starts at the source, comes down, shoots out. It can't go this way, so it goes that way, comes up, goes out this way, comes down, and around. So now let's figure out what that does. Okay, I'm going to bring back my pen and choose my color for. Now, let's look at both half waves, right? This is editing on the fly. So what happens then? Okay, so we already figured it comes here, goes there. That means this one has that. And it comes out to this point. Comes back around, goes here, comes down that way, does that, comes out back to there. The negative half wave, I'm using red for that, so I'll continue doing so. Negative half wave comes down here, goes this way, goes to there. Now we have this. Changing things. There. So now we have the negative half wave, right? Now the reason why this is flat to begin with is because during the positive half wave, it was up here, right? There was no power down here because our source doesn't look like this, right? If we draw out our source, it's not making ovals. It might be like, how would you even draw that, correct? Because it doesn't work. So we're not doing that. It has to have an empty spot. So at this point, it's 0, then it goes, and then it's 0, and it goes. Comes up, comes here. Now this adds to the last one. Right? Comes up and around, comes back. Now it goes up this way. Means we have the same thing. Up this way, out and back. And there, as you see, we have the circuit that we were expecting, or the signal we were expecting come out of the circuit. That is exactly how the normal usage works for a half wave or full bridge rectifier. So now let's look, what else can we do with it? Well, I mean, we have lots of spots. As you see, I marked these A, B, C, and D. We actually have 6 ways that we can connect these together, right? A to B, A to C, A to D. Now we have C to D here at the bottom. Why didn't I write like D to C, D to A? Why aren't those there? It's because we know that positive and negative voltage only changes by reversing the probes. So instead of writing these, I can make my life a lot easier just by saying DC equals negative CD. It's going to happen every time. I don't need to worry about it. So that's why we have that. So let's take a look and see what we've got. Like, can we figure out what's actually happening in these cases? All right. We could start with AB, but you know what? I'm going to start a little bit out of order in this list because I made the list just alphabetically, and I'm going to go jump to ones that are like simple. Okay. So first, I'm switch back to my pen because I had to switch back and forth a lot, and then I want to write in that blue color because it's soothing. Nice. Okay. So what's the easiest one? Well, there's AC. What is that? If you look at A, it's connected to this point, which is connected to this point. And look at C, it's connected to here, it's connected to there. So that means that AC is literally just measuring the input. We know what that is. That's sine wave, right? Bam. Easy. Okay. There's another easy one. Well, we've already determined that BD gives us our signature lumps, even though for some reason it keeps trying to erase my stuff. I don't think I like PowerPoint with my pen. Okay, so that means BD gives us this. All right, how about the other ones? The other ones seem a little more complicated. A to B. Well, we already established that through this through this diode, we have this wave. That is the wave that comes out. So that is the point that's located at B. The point coming in, we just determined, is a sine wave. Okay? So if we want to know what drops across this diode, all we have to do is take our sine wave and subtract our output. So as I said before, the voltage between 1 and 2 equals the voltage at 1 minus the voltage at 2, right? So here we have the voltage at A, which is a sine wave, minus these half lumps. These obviously correspond with these because that's how it comes through. So that means the only thing we're left with is the bottom half. So the bottom half lumps are all that's left. Yeah, easy enough. Next, we have A to D. We have the point A. I keep on grabbing the wrong thing, sorry. We have the point A right here and the point D right here. So earlier on, we established that during the negative half-wave cycle, this conducts. So we have a flat, and then a lump, like that. Here, we have just lumps. So, if we have from A to D, this setup, we need to take A and subtract D. All right? Same thing we've been doing this entire time. We know what comes out of it. This comes out of it. This is what goes into it. We need to figure it out. So if you take these and subtract them, you get this. Hopefully that makes sense to everybody. Now, the next one, B to C. Okay. Once again, we established this one's a negative half wave, so it only conducts on the negative side. We know the output is this. So now we need to take the output minus what comes through, and we get this again. Obviously, right? Okay. Now, one more left. We have C to D. On this one, it was a positive half wave. So I'm going to change back to blue just so we can keep that clear in our heads a little bit. And it's lump. Once again, we have the exact same system we've used the other 3 times, and we end up with underscore lump underscore, right? So what does that mean? What can we do with this, right? We now understand where everything is. If you look at this, you can see values that can be useful to you. For instance, your project that you're likely working on has you working with 12 volts and minus 12 volts. So if we were to combine these, possibly we could get our different signals without having the drop across the entire thing be 0, right? Because if we take the setup, we take this, that's actually not what I want to say. Sorry, let me rephrase this. If we take this and subtract that from it, what do we get? We have 0 volts. That is not what we want. Okay, what we want to have is we want to take this and subtract this, right? Because at that point, we'll have a peak to peak of 24 volts. Volts peak to peak, right? Terrible writing, I know, I'm sorry. So, if you look at these, you're trying to point with a pen. If you look at these, there's some obvious candidates here. There's one that's very obvious, right? We have A to B and A to D. So they both share A as a common spot, and then it goes up 12 and down 12. That's good. That's one thing we want. There's another one here that's not as obvious, but using our rule here, says D to C equals minus C to D, means that we have the exact same situation as this here, where C is the common, and then B is high and D is low. Okay, that makes sense to everybody, right? So, let me draw a couple things for you. We have pen, okay. So what we're looking for is this voltage with a reference of this Now, if you look at that, then at that point you have sine wave. The average of a sine wave at any point in time is going to be 0 volts. So that's not going to be helpful for us, right? So what we need to do is find a way to get it to come up to this point and then just stay there, as well as come down to this point and stay there. Now, if you remember from earlier, let's say we have this as an input at this line, right? So if we have this, we should stop doing that. Put a capacitor here to ground, come out, and here we have our load resistor. This capacitor, after it charges, acts as a voltage source. And what it will do is it will smooth out this value, if you remember from labs, right? So it comes up and that becomes your signal. You do the same thing with the other one. Keeps thinking I'm right-clicking and holding when I'm using my pen. I don't know what's the deal with that. All right, take that as the input. It gets its own capacitor to ground. That comes in. That's your RL. And at that point, you have this. So if you compare this point to this point, you'll always get your full 24 volts minus your diode drops that we're ignoring at the moment. Okay? So then what's ground? Now remember, ground is only a shortcut for a reference. So in order for that, you need to have a common reference between the two of them. Otherwise, you can't measure the distance between the two of them, right? I think you might have found that in lab as well. So if we look at the last slide, you see a common point. Let's use these two because they're already facing the right way. A common point that they have is A. You see they both share, back up the laser pointer, they both share A, okay? So that means if you connected A out, I wish I could point with the pin. So if you bring A out and then call that the ground, ignoring this ground symbol because whatever, it's only there for multi-sim reasons. Bring that out, call that the ground. Then if you measure in between A and B and A and D, so we have B and we have D, you bring this one out as well, and you bring this one out. Then between these you will have 12 volts and minus 12 volts. And that is generally one of the secrets to the project that you have been working. All right, guys. I hope this has been helpful. I know it's kind of rambling. This is a difficult one. I've actually tried to record this video probably about 6 or 7 different times. At first I was going to do it like I did the Zinner video, and it was fighting me. And so finally I had to make the PowerPoint that already had everything in it, because I'd find I'd get about 20 minutes into the video explaining everything and drawing it out, and then I'd make a mistake and things would be all screwed up and confusing and I'd have to start over. So I apologize if this is confusing. I'm trying my best here. If you have any questions, please feel free to email me or leave a comment in the video or whatever, and then I will do my best to help you out. Thank you, and have a good one.